Hey everyone, welcome back to physics. This will be lecture 16 of the course. And this will be a shorter lecture. We just want to hit on a topic that'll be very important in the coming sections where we're going to try to apply Newton's laws to a variety of problems. And that topic is the free body diagram. So let's take a look at this. So we'll call this section 3.5, free body diagrams. Now, we just got done talking through Newton's three laws, high level, and we've done a few examples. And really, Newton's three laws of motion contain really all of the basic principles needed to solve a very wide variety of physics problems. However, that being said, although the physics are fairly easy to understand, well, at least at high level, applying Newton's laws may not always be easy. And really one of the most important tools in solving actual physical problems using Newton's laws is the concept of a free body diagram. So specifically, when we think of Newton's first law, of course, is the objects at rest will remain at rest unless acted upon by an outside force, and objects in motion will remain in motion unless acted upon by an outside force. So in the case of the first law, we are talking about a specific body. So this is about a specific body. Now this is also true of the second law, right, which says if there is a net force, i.e. if the sum of the forces acting on the body are non-zero, then their body will be accelerating, and it'll be accelerating according to this relationship here. This law also is about a specific body. Right, so the first law and the second law both describe motion regarding a specific body. So given the forces, you don't know the forces, then these laws will tell you what's going on with the body. Now, Newton's third law, of course, is not about a specific singular body. It's about a pair of bodies and how they react to one another, how the forces are equal and opposite. So really, the free body diagram is the most valuable in the case of Newton's first and second law. So what is a free body diagram? What is this thing? A free body diagram. It's a diagram that shows the relevant body. It shows the relevant body, i.e. the body upon which forces are acting and upon which there's some acceleration, right? Or maybe no acceleration, whatever the case may be. So a free body diagram is a diagram that shows the relevant body, almost always singular, free from all but the forces acting on it. Okay, so basically a free body diagram takes the body of interest, like maybe it's a car, maybe it's a person, maybe it's a bowling ball, maybe it's a crate sliding across the floor, whatever happens to be the case, takes that body of interest and maps onto it all of the forces that are acting on it. We don't care about where the forces are necessarily coming from except in labeling them. We don't care about what forces this body is exerting on other things. We only care about the forces that are being exerted on this body. Okay? And the free body diagram will typically display just that body and the force vectors, both magnitude and direction, acting on it. So the diagram will display the body and the force vectors acting on it. Right, and when I say force vectors, I mean the magnitude, relatively speaking, and the direction, of course. So the magnitude and the direction. We'll need both. Okay, so let's take an example. These are actually very simple diagrams, but they can be complex if the situation is complex. So let's take a simple example here of a diver. So a diver is sinking slowly in the water. Right, so we've got the diver, we've got this body, we'll call it the diver. Right now, if you don't in practice have to label the actual body itself, but just in our case, we're going to do it. So what are the forces acting on the diver? Well, you've got mg, right? Mass times gravity, i.e. the weight of the diver. Now this is going to be the same as anywhere else. The fact that the diver happens to be in water doesn't make the diver actually weigh less. What actually happens in water is you have an opposite force that's not the same as the normal force, but operates in a similar way. And we're not going to get into the details of that, but it's a force called buoyancy. Okay, so B here is the buoyancy of the diver. So B-U-O-Y-A-N-C-Y, buoyancy. Okay, so this is the various, different, as you know, different types of objects, masses will have different buoyancies. Human beings have a certain amount of buoyancy. Rocks have quite a bit less buoyancy. Chunks of wood have lots of buoyancy, etc. Right? And so buoyancy will vary depending on the object, but that's really what's happening here. So you really do have the force of, the diver's weight pulling them down, and then you have the buoyancy offsetting the diver's weight to some extent. Now this isn't a great free body diagram because it does say that the diver is sinking, and the implication there is that actually mg is somewhat larger than b. Right? So specifically mg would be greater than b if the diver's sinking. Right? So I guess that's not great. This one, something to make it really clear that the buoyancy vector is shorter than the mg vector. Okay. Now sometimes the magnitude of the vectors isn't the most important thing. But it can be. I mean, if you know for sure that the diver is sinking, and that's a piece of information you could land in your free body diagram by just making the vector shorter. Right? And maybe it's better even to exaggerate it. Right? So you've got your mg, and maybe you've got your b. Just so you know clearly, diver is sinking, since that information is given. Right? But this is a free body diagram. Notice we're not concerned about the water around the diver. We're not concerned about the diver's flippers. We're just thinking of the diver as one body, and there is the weight of the diver and the buoyancy of the diver, and those are the relevant forces. Now, with regard to free body diagrams, we never consider internal forces of a body, the heart pumping, the muscles twitching, whatever. We don't worry about that because we're really only worried about the forces that are externally exerted on the body. Okay, so that's a good first example. Another example, frequently free body diagrams can display before and after information to kind of help describe what has happened to a body. So here's a very simple example. A person is standing on solid ground one moment, a person is standing on solid ground one moment, and then after jumping, is midair. All right, so two instances, a before and an after. So let's think about the before. This is the simplest kind of free body diagram you're likely to see. So you've got mg operating on the person, and you've got the normal force of the ground pushing the person, holding the person upright. And the two forces are opposite directions. They happen to be equivalent in magnitude, and so the person is not accelerating. That's before. Then after, the person, so in between here, the person jumps into the air, and what does the free body diagram look like then? So we're presumably when the person is midair, what does the free body diagram look like? Well, there's no normal force, but you still have mg, don't you? All right, mg hasn't changed. It's the same, but there's no normal force because the person is midair. Right, and so here you're going to clearly have a net force, and specifically downward. So you'll be in what we call free fall. Right, the only force acting on this body is the force from gravity. Okay, so frequently you can use free body diagrams in a before and after kind of scenario. So you're standing, you jump, and then what's it look like? All right, so that's, again, pretty simple example, but really the key here is just to think about these diagrams and to be able to draw them, right, given any situation. So how about a slightly more complex situation, one that's got a little bit more complicated free body diagram, and that'll be the runner at the starting line example. So a runner starts a race. A runner starts a race by pushing off against angled starting blocks. Okay. She pushes against the blocks, and as we know, the blocks push back against her. So I'll put this in here. She pushes against the blocks, and the blocks push back against her. Okay. All right, so that's almost like subtext, right? So the runner starts a race by pushing off against angled starting blocks. She pushes against the blocks push back against her. What does the free body diagram look like at the start of the race? So what does the free body diagram look like at the start? Right, so at the instant the runner is kicking off, basically pushing off, and therefore the block's pushing off against her. So what does the free body diagram look like? Well, let's think about this. We've got the runner. Right, we know that the runner is feeling the force of gravity. Now, there's always a normal force, right? Right. I mean, assuming the runner isn't accelerating downward, right? We'll just assume this runner is going to be accelerating in the horizontal direction, not up or down. So there's going to be some normal force here, and we'll say, just as per usual, it's of equal magnitude to the weight of the runner. Okay. Now, what about this force from the blocks, right? So she pushes against the blocks, and the blocks push back against her, right? So there's a force coming from the block, right? And it's not purely horizontal, is it, right? Because these are angled, right? If they were purely horizontal, then we would probably draw the force in a horizontal orientation. But actually, these have some inclination to them, don't they? So they kind of come up like this, we'll say. And I'll just draw it nice and long like that. And we'll say this is the force of the block. Okay. Now we can really think of the force of the block as being basically like a normal force. She pushes against the block pushes back. So I'm going to actually label this as N. But we know that this is at an angle, and so technically it's going to have an X and Y component, right? Right, so you can kind of think of this. And so really this piece here, so she kicks off the blocks, and the block's is going to push back with an X component and a Y component. And this guy here, I'm gonna label N sub X. So this is like the normal force from the block pushing her in the X direction. And then this guy here, I'm going to label N sub Y. So this is the force from the block, the normal force from the block, pushing the runner in the Y direction. Now the length of this guy here is actually the same as this, so this is the same force. All right. So the angled block accomplishes what? Well, it accomplishes, when you kick off, it accomplishes both keeping you upright, i.e. overcoming the force of gravity, keeping you upright, but also because it's angled, you can use that same force to help propel you down the track. So not everything in that initial kick is propulsive. Some portion of it's just keeping you upright. And that's what this free body diagram really helps illustrate. So whatever this force is, this force that the block exerts on the runner's foot, you have to figure out what part of that is going into the down track acceleration, and what portion of it is offsetting the weight of the runner, i.e. gravity. Right? And so in this case is a little more complex. This is a little more complex, and so the free body diagram is really helpful here. Right? So the force that the block exerts on the runner is partly horizontal, right? And that's going to create the motion in the x direction. But part of that force is exerted on the block is in the vertical direction, and that's going to be this piece here, which offsets the runner's weight. Okay. And so this is a nice example of a free body diagram. And so if we were asked to figure out the acceleration of the runner, and we're maybe given the force that the block exerts on the runner, we could figure out whatever, given this angle, we could figure out what this force is here and calculate an acceleration using Newton's second law. Okay. All right, so those are just a couple of examples of the idea of a free body diagram. We will use them throughout the coming section. We'll use them in chapter 4 where we talk about applying Newton's laws. Really, we'll use them throughout probably the next 24 lectures, maybe even beyond. So that's just a brief introduction to that, just so you know what I'm talking about when I say let's take a look at the free body diagram. Now you know what that term means. So all right, we will end it there, and we'll talk to you all next time. Take care.